Welcome to the 22nd video of this course on quantum processing. Today is about Rydberg atoms. So let's begin from this simple equation from quantum electrodynamics. You know that the G as a coupling constant between the fields, between photon field and two-level atom. You have the dependence of this G coupling constant on the volume of the cavity that includes this atom. So if I would like to increase the coupling constant, I may reduce the V by dependence on the square root of V. So G is inversely proportional to V, the volume, and G is also directly proportional to the dipole matrix element that can drive the transition for this two-level atom in this system of quantum electrodynamic system. Let me tell you something important also. For this relation of the energy, you can express the energy of your Rydberg energy in terms of the dependence on n square, but remember this quantum defect point, quantum defect from atomic physics has to exist. So let's consider that I have an atom. This atom can be rubidium, can hydrogen, be sodium, whatever, and you have the nucleus and the hydrogen. Let's take the hydrogen. So you have the hydrogen, n is equal to 1. I'd like to excite it to the n is equal to 50. So the principal quantum number 50. This is a huge excitation. So this is what we call the Rydberg atom. The Rydberg atom is a very highly excited state, so to the most, maybe the highest excited state that you have in your system, if you would like to excite. So this is what we call the Rydberg atom, something like this. To the shell of principal quantum number 50, like what I told you now. So if you look back to this equation again, you can drop this term here for the quantum defect, because it's small comparable to this n, so it becomes the known equation for the R over n square dependence here for the energy quantum numbers n and l. If you calculate the matrix elements of dipole matrix elements between two wave functions of the ground state and the excited state, you can see that for this kind of excitation you have dramatic increase of the principal quantum number here. So here you have increase for n square. So it means that huge dependence on this n of this quantum number excitation that you can raise the atom from the ground state to it here. For the Rydberg excitation, for such Rydberg atoms, you have dramatic also increase of the van der Waals interactions between two atoms that are excited to the Rydberg state. So it scales with the 11th power here for this van der Waals interaction. So van der Waals extremely increased by this kind of excitation that we have. Okay, so let me show this important model. Let's take for first Rydberg excitation. So let's see how Rydberg excitation happens. If you have two atoms, let's say stick with one atom for example first. Okay, if you have one atom, you'd like to excite it to a specific state. You have this coupling, wavelength, this frequency, Rabi frequency that we introduced before. And remember that you have also the tuning around this, like what we presented before in last video. We introduced the idea of Rabi frequency. We introduced the idea also of the tuning around the frequency of the excited state. So here you have the ground state, and here you have excited state. So let's think of two atoms. If you have two ground state atoms like this, okay, and you start to play with the energy, you raise it to the here you have in between the excited state, the full excited state, and the two ground states here for the two atoms being in the same superposition state here. You have the superposition between the ground state and the excited state, and also for the other atom. So let's say that we excited our atom, or two atoms here, from the ground state to the excited state, like this. Okay, and let's say only one atom is really excited, and you can have whole this scan of R dependence between atoms here, the R distance between atoms, and once you see this relation is true, because if you have the distance R exists at this kind of energy, and you start to sweep from right to left here, you find that you are not allowed to excite more than this. for the other atom. So it means that now you have a block here for this excitation. Here is called the blockade radius. That means that I only can excite a single excitation, single atom. I just excited one atom to the Rydberg excitation, and the other atom is forbidden. But I can do this for this also transitions for the other atom if I have isolated those atoms in a size, okay, which is much smaller than the Rydberg blockade radius here. So I can take a system, a full system. I can make or I can isolate many atoms that I would like to excite, but we have to make sure that the blockade radius is much larger than the distance between those. So I just have to keep in mind this blockade radius in order to make this kind of excitation around here for this Rydberg excitation. So if I have one single excitation, or whatever kinds of excitation I have in our atoms, so I can write down this coherent superposition between many configurations that I have in my system. So in fact, I can have many coherent superposition for this, what we call the superatom. Here it's Rydberg superatom. I call it Rydberg superatom. Okay, and remember that the blockade radius also is kind of important. I have to make sure that my excitation follows, and the Rydberg excitation for the blockade radius, it actually is inversely proportional to the frequency, to the Rabi frequency. But remember, this is square root for 6. You find this in many textbooks talking about Rydberg. So this comes from the van der Waals dependence on the sixth power, as you know, for van der Waals interactions. What's interesting for these Rydberg atoms that you can study many long interaction schemes. Okay, you can isolate a single atom, maybe two atoms, to maybe 20 or 50 or 100,000 atoms. They are in multi-insulator state, okay, and you're taking them one by one to excite single atom one by one until you reach a coherent superposition between many configurations for this Rydberg superatom. You can study long-range interaction. This is the Hamiltonian here. This Hamiltonian this Hamiltonian contains the features of the coherent coupling here between the grounded state and the excited state of your Rydberg ground state atoms. And here you have also the kind of, you have put all the atoms, or two atoms, let's say I and J, okay, I here, the atom, the other atom is in J, and you have both this, remember this sigma representing the ladder operator for our ground, or for ladder operator for ground and excitation states that we have, and for our light we have the A dagger, just the common notations. And here for this term we said this is the coupling here, this is the van der Waals repulsion interaction between two atoms here. So this Vij is the responsible term for the long-range repulsive interaction, extremely extremely powerful, extremely strong interaction, extremely strong repulsive interaction between the Rydberg atoms. And here nothing else in here, just the tuning for the here laser, and here this is for the chemical potential. Let me write down this here, coherent coupling, and here for repulsion, and here for the chemical potential. From this Hamiltonian, this is what we call the long-range interaction quantum Ising Hamiltonian, quantum Ising model, and you can get this model to study many correlation between different atoms held, for example, in optical lattices. You can study Rydberg atoms excitation. You can study the dynamics of different atoms in superposition state, and they are considered to be frozen gases. They are considered to be frozen Rydberg systems, frozen Rydberg atoms. Mechanical, there is no mechanical motion actually in the time scale of the dynamics. This model is studied a lot in quantum optics, so you can go to one of the papers of Sergio Rausch talking about exciting the atom, and or even the name of the paper was called "Seeing a Photon Without Destroying It." I will link it below to the video here, so you can check it out. that you can singly isolate a single atom and you put it in a cavity and its atom is in excited Rydberg state, and you start to shower some light to see this kind of excitation of absorption of light, but without destroying the photon states. Okay, you can check this paper. Also Rydberg for different kind of experiments in crystallization and realizing Rydberg crystals and all of these nice features. But this was just a video introducing the main concepts of using Rydberg atoms in the context of quantum Ising model for these terms that we introduced here for you. Thanks for watching and see you in the next video.